of meromorphic GL2C connections, please.
Okay, thanks a lot. I'm really to be invited to Friday Fish. Awesome seminar, wonderful objectives. So yeah, I'm all for it. Okay, so I want to tell you basically. So I mean, this was the main problem from my PhD thesis, or part of the main problem for my PhD thesis, and it's based on a paper, which is the first paper that came out of my PhD thesis, like a year and a half or 2 years ago. 2 years ago now, time flies. And then I've sort of been extending it in a variety of ways. So that's kind of what I want to tell you about, with the caveat that the kind of more recent work in progress, I'm quite confident that it's correct, but of course, as any work in progress goes, there might be some red herrings. So with that caveat, I will proceed. Okay, so I'll fix some things. So I'm always working on a Riemann surface, usually compact. That's called X. And let's have a look at a holomorphic bundle on X, which if you are more...
Nikita, you're like, I don't know, with something wrong with your microphone, but your sound gets distorted.
Oh, really?
Once in a while.
Oh, well, that's annoying. How do I fix that? Let's see.
There is an echo, so maybe it's...
If it happens again.
Right, okay, so yeah, I'll look at holomorphic vector bundles on on X. And if you're more kind of differential geometric minded, then for you, this will be a sheaf of holomorphic sections of a holomorphic vector bundle on X. So to me, those two things are the same. And the other thing that I'll fix throughout is a divisor on X, an effective divisor. So in other words, that's just a discrete set of points, finite if X is compact. But importantly, these points carry multiplicity. And so basically, I'll be considering meromorphic connections, so they're singular objects. And these points D are exactly where I'll allow my connections to develop singularities, and the multiplicity will be exactly the how bad I allow my singularities to be. So a definition, so a meromorphic connection on a vector bundle E is a map on sections, sends sections E to sections E tensored with differential forms. So this is a notation. These are differential forms, holomorphic differential forms with possibly poles at the points of D with some multiplicity, where this thing is holomorphic. So this is a map. It's not linear on functions, but it satisfies Leibniz rule, which is what makes it into a differential operator. So just to recall, Leibniz rule just means that if I take any section E of the vector bundle and multiply it by a holomorphic function, and I apply nabla to that product, then there is a term which is linear on the function, but then there is a correction which depends on the derivative of f. So D is the de Rham differential. Okay, so locally, these things are so if I pick a local trivialization of my vector bundle, then these things are literally just the de Rham differential plus an endomorphism phi, endomorphism valued in differential forms. So it's differential forms with poles. So it's it's a singular endomorphism. And in particular, if we focus even more locally on a specific point P inside the divisor D, and that point has some multiplicity, 1 or higher. And let me choose a coordinate Z, which is centered at that point. Then in that coordinate, I can write my connection as something even more familiar. So D plus a matrix, literally a matrix of holomorphic functions A of Z, times this differential form element, dz over z to the m. And again, like even more concretely, these are really your favorite differential equations, classical differential equations that you encounter in whatever first year, second year, undergrad. So if I take still working, let's say in this coordinate, and if I look at the covariant derivative, so I input a vector field d by dz, then looking at these connections is the same thing as looking at differential systems of first order linear coupled differential equations, singular. Again, they're singular because I have this, the equation is technically not, well, it experiences singular behavior at z equal to 0. Okay, and so actually this expression is kind of important because one observation you can make is, well, if I look at the covariant derivative and I shove in, I apply it to holomorphic sections of E, then I necessarily get something that is meromorphic because I have this 1 over z to some power behavior. But if I actually, if I look at covariant derivatives where the input is not a vector field, but rather not a usual vector field, but rather necessarily a vector field which vanishes to some order at this point z equal to 0, then that would counterbalance this singular behavior at the origin. So that's the observation, that if we plug in not the vector field d by dz, but these special vector fields, they're special given by the divisor. The divisor has these points and multiplicities, and it tells you which vector fields vanishing at these points you need to consider to what order. And the point is that once I put this kind of vanishing vector field, then this covariant derivative becomes a map, an honest map from holomorphic sections of E to holomorphic sections of E. I get nothing singular. These vector fields, these kind of vanishing vector fields, they're very famous objects, and the most important fact about them is that they form a Lie algebroid on X. It's a rank 1 Lie algebroid, which is just the tangent. It's called a twisted tangent bundle, holomorphic tangent bundle. So these are vector fields, holomorphic vector fields, which vanish at the points D to the specified multiplicity. And the anchor map, well, of course, any such vector field is in particular a vector field. So the anchor map is literally just the inclusion. So it's a very simple looking holomorphic rank 1 Lie algebroid. They're actually, at least when you're sitting on a Riemann surface, they're actually ubiquitous. There's this very simple fact, which is that if I look at a Riemann surface X and I want to understand all possible rank 1 holomorphic Lie algebroids on X, then it turns out that unless the Lie algebroid that I picked is just a bundle of abelian Lie algebras, which is not very interesting, then this Lie algebroid has to be one of this form. So it has to be the tangent bundle twisted by the divisor. Right. Okay. So because we are on a Riemann surface, it's a complex manifold of dimension 1. There is no curvature. These connections that I am considering necessarily have no curvature because they're holomorphic connection or meromorphic connections. And but the curvature is a degree 2 differential form. And on a complex manifold of dimension 1, there are no degree 2 differential forms. So curvature just trivially vanishes. And of course, having no curvature is the same as this equation, which you can interpret as being the fact that the covariant derivative, interpreting my connection as a covariant derivative, it preserves the Lie bracket. So it's a Lie algebra homomorphism. And so therefore, for this reason, meromorphic connections are called representations of such a Lie algebroid. So basically, these are the things that I want to study. So meromorphic connections, I want to view them as representations of these kind of Lie algebroids, which are twists of the tangent bundle. And of course, you can also transport this to the realm of groupoids, Lie groupoids, by integrating everything. So these Lie algebroids, twisted by a divisor, they have integrations. You can pick the source simply connected integration, and that is usually called the twisted fundamental groupoid. So these things are, so away from the singular locus D, away from the divisor D, they are just like the usual fundamental groupoid of homotopy classes of paths. But then over the points in D, they're kind of certain blow-ups of action groupoids. And kind of more practically, they basically consist of limiting paths that limit into the pole in some very specific way. So these are sometimes called, or not sometimes called, they're called Stokes groupoids, introduced by Gualtieri, Lie, and Pym. Right, and then, so the Lie algebroid integrates to this specific Lie groupoid, and then the Lie algebroid representation, which is my meromorphic connection, that integrates to a Lie groupoid representation. And this representation is basically just parallel transport of my connection, which, away from the singular locus, that is completely obvious, but then you need to be a little bit careful when you're in the singular locus, because you need to kind of take these parallel transports along these very specific limiting paths. But anyway, as usual, this Lie groupoid representation is then a Lie groupoid homomorphism from this twisted fundamental groupoid into the gauge groupoid of my vector bundle E. And it's a kind of like a universal parallel transport for my meromorphic connection. Okay, so there's a bunch of operations that you can do with meromorphic connections or with representations of Lie algebroids or groupoids. One that I particularly care about is called a push forward. So if you have a covering map, so two Riemann surfaces, degree n branched covering, and you start with a meromorphic connection on Y, you can push it forward. So to be a little bit more precise, so here I'm denoting this covering map by pi. The covering Riemann surface is Y. And I introduce notation for the branch locus and the ramification locus. And just for simplicity, let me assume that they are simple, which means that at any one point, only two branches of the Riemann surface Y meet. And in that fiber, that's the only ramification. Right. So I can look at representations of a Lie algebroid on Y, which again are going to be vector fields vanishing along a divisor. So let me consider a divisor which which is the pullback of the divisor D from downstairs. And importantly, I'm pulling it back as a divisor rather than as a subset. So I'm carrying with me all the multiplicities. So that's this guy. I could also include the ramification locus. Actually, I will have to include the ramification locus to it. So yeah, anyway, so let me consider this Lie algebroid, which is vector fields on Y vanishing along this effective divisor. And it turns out that once I have this setup, then indeed I can push forward representations of AY to representations of not quite AX, but something a little bit more complicated, which is I will also need to twist AX by the branch locus. So in other words, if I start with a connection on Y and I push it forward, I get a connection on X, and that connection is necessarily going to be singular at the branch locus. This is somehow unavoidable, and I'll mention it again in a minute. So in particular, this is the case that I really want to focus on. In particular, if I look at rank 1 representations on Y, then I can push them forward. And basically what, the starting point is you first take the line bundle, that would be the rank 1 representation, and you push that forward. And because the degree of the covering map is n, the push forward, which is basically a sum of all the lines in the pre-image, in the fiber, and you have to work above the ramification, but kind of where the covering is trivial, it's very easy to see that pushing forward a line bundle, you get a rank n vector bundle. So basically you get this push forward map that you start with rank 1 representations on Y, you push them forward, you get rank n representations on X, which are singular at the correct loci. And so this is kind of cool because rank 1 representations are really, really very simple. I mean, especially thinking of, let's say, them as representations of Lie groupoids. I mean, they are just abelian, C star representations. They really are quite simple. Whereas rank n representations, they're representations into GLN, a non-abelian group. So somehow when things are non-abelian, we all know it becomes harder. So one question that you could potentially ask
Can I ask a small?
Yeah.
So the ramification, the branch locus and the device you start with, like, can they have non-trivial intersection, or? Yeah,
at this point, yes. But in a minute, I'll actually want to separate them. I'll want to make sure that they're separate. But yeah, for this push forward, there's no problem if they intersect. Yeah. Right. So yeah. So you could ask a question: can I use this push forward operation to actually recover every representation on X from some appropriate rank 1 representation on a covering Y? This would be very advantageous because then, if I can present a rank n representation as secretly being a rank 1 representation just on a more complicated Riemann surface, then I could rephrase all my non-abelian problems about rank n representations as abelian problems about the rank 1 representation. But of course, life is not simple. The answer is that absolutely not, you cannot do this. There's many reasons why you cannot do this. One extremely important reason, which is it seems to be very difficult to get rid of, is the fact that whenever you start with let's say a rank 1 representation on Y, so that's my connection del, connection on a line bundle, and I push that forward, I get a rank n representation on X. So not only is that thing necessarily singular at the branch locus, it also has a very, very special type of monodromy around the branch locus. It's what is called the Quasi-Permutation Monotomy, and that is basically it's basically dictated directly by the covering Y itself. So covering Y, because it's branched at that point, it has an associated monodromy, which is some kind of permutation monodromy. And then this quasi-permutation monodromy for the push-forward connection is essentially the same thing as this permutation, which kind of means that, for instance, if you want to get a connection which is smooth at the branch point, non-singular, you cannot do this because the monodromy of the push-forward connection is the permutation representation of the covering. So unless the covering is trivial, which means it's not a branch point to begin with, then you simply there's no holomorphic transformation that would take you from one to another. Okay, but yeah.
Is this only true if we assume that the original rank 1 connection was smooth on the ramification?
No, it's always the case. By changing the residue, so by by assuming that the connection del is singular at the ramification, then it would have a residue, and that residue would just show up in your quasi-permutation representation. Yeah, so there's no way to remove it. Right. Okay, but of course, there is something we can do. Otherwise, I wouldn't be telling you about this probably. So there is a goal. It's a kind of big project goal, and I'll tell you only about a relatively small part of it. And the goal is to kind of come up with an ingenious way to make correct assumptions on the covering surface Y and the divisor and all the other data involved, such that there is some kind of equivalence between rank 1 representations on the covering and rank n representations on the base. This is somehow not insane. I mean, we have examples of this. So if any of you are familiar with, let's say, Higgs bundles, this is directly motivated by something that you see in the theory of Higgs bundles, where this thing called spectral correspondence, where you basically have a Higgs bundle on a Riemann surface X, and it is equivalent data to a rank 1 Higgs field, Higgs bundle, Higgs line bundle on a covering Riemann surface of degree n. So, I mean, this is just basically just a very fancy way of saying that if you have a matrix, an n by n complex matrix, you can diagonalize it, and whatever, with correct assumptions, you can diagonalize it, and knowing, the diagonal entries are just the eigenvalues. Knowing those eigenvalues, you basically know everything you need to know about your matrix. So this is what I said about the spectral correspondence is in some way the same story, just in families. And right. Okay, so these two categories of representations, they have I drew some kind of decorations on them. I'll explain what these are, but basically this category of rank 1 representations on Y, I need to restrict it in some way. And it turns out that the correct thing to do is to fix residues along a ramification. And then on the other side, I also have to make some restrictions on the kind of connections I can consider. And those are basically some kind of genericity assumption with respect to a combinatorial gadget, which I will assign to my Riemann surface X. So I'll explain, the point of this talk is to try to explain all this. Okay, and then maybe I could state it as a theorem, which is that if you, whatever the definitions of these categories are, I'll explain, but at least for n equal to 2, so when we consider double covers of Riemann surfaces, then indeed you can build such an equivalence, and that's what's called an Abelianisation. Okay, any questions about this so far? Okay, so, right, so in order to explain this, basically the main thing to explain is this decoration gamma. So this is some certain combinatorial object that I need to pick on my Riemann surface X in order to proceed with the construction. So in order to explain that, I need to explain something about meromorphic connections. Jan, you have a question?
Sorry, can I have a question? So you say that this image of this pi star, these have very special the very special monodromy around those B's.
Mm-hmm.
But then you say that these rep gamma, they are in some sense generic inside all the 5 connections.
Right.
So it's true that so this very special quasi-permutation monodromy is also in some sense generic in all the monodromies?
I'm not, maybe a more correct way to kind of explain what's going on is that it's not that it's generic amongst these connections, is that it's the monodromy for these push forward representations is of a very standard form. So standard, in fact, that it can be encoded into a certain cocycle, which then acts on the push forward functor to deform it. So basically, kind of the idea is that the push forward functor, pi lower star, is broken because the push forward connections necessarily have this quasi-permutation monodromy at the branch locus. So the construction is to modify, locally deform this push forward functor into a different functor, which somehow lands in the right place. And the reason you can do that is because of the observation that the way these push forward representations behave at the branch locus is somehow very, very standard, that it doesn't, the behavior itself can be encoded into something that doesn't really care about which representations you pick, and therefore is applicable to all representations in a functorial way. So that's roughly,
Yeah, thanks.
Okay, so there's something, some kind of very important, essentially Lie theoretic data that you get with meromorphic connections when you restrict to the irregular poles of higher order. And that data basically manifests itself as certain directions emanating from the higher order pole, and I will use those directions in my construction. So let me kind of go through it maybe relatively quickly, but just to kind of, anyway, so let me look at a point P. It's a pole multiplicity M. M could be 1, 2, or higher. Then what I can do is I can look at my Lie algebroid, the anchor A, going from the Lie algebroid to the tangent bundle, and I can restrict that map to the point P. So now it's a map of Lie algebras, and I can look at this kernel. That thing, by definition, this is called the isotropy Lie algebra, and there's a fact, a very useful fact, which is that it is isomorphic, canonically isomorphic to the m minus first symmetric power of the cotangent space at P. And the reason that's true is basically you need to look at jets. So my anchor map vanishes at the point P to order M. This is what is meant by multiplicity, M. So the anchor map vanishes to order, sorry, not M, to order M minus 1. It vanishes to order M minus 1. This is what is meant by multiplicity, which means, the anchor map vanishes to order M, which means its M minus first jet is 0, but the mth jet is not 0. And so when you look at the mth jet sequence and take an appropriate quotient, then you get precisely this cotangent space. So that's where the cotangent space comes from. Okay, so if I have a representation now of this Lie algebroid, then I can look at the corresponding isotropy representation, which again is just restriction to the fiber. And what I get is just an endomorphism of the fiber of the vector bundle above P. In a kind of really down-to-earth language, if we're thinking of connections in local presentations as whatever differential equations, then when the pole is a simple pole, so M is multiplicity is equal to 1, then this isotropy representation is just the residue matrix of my connection, just the matrix that is above Z to the power of minus 1, which is, of course, an endomorphism, well-defined endomorphism of the fiber. And then in the higher rank, it's again, it's maybe it's a bit more complicated, but it's the leading term of the principal part. So if the multiplicity of P is M, that means my connection matrix, the matrix of my connection is the leading term is dz over z to the m. And in front of that term, I have a constant matrix. So that's the leading order term, A0. And again, that is an endomorphism. It's an endomorphism of the fiber, but now importantly, because it has this dz over z to the m, it's not quite just considering the matrix A of 0. That's not quite a well-defined object geometrically. What is well-defined is it's the isotropy representation. So it's you really have to consider the matrix valued where the entries are valued in m minus first symmetric power of vector fields. But okay, so it's an endomorphism of this vector space, which is the fiber of E at P, valued in some other vector space. This gives me distinguished elements of the symmetric power of TP, which is just eigenvalues of my isotropy representation. And if I look at the adjoint action, that basically just amounts to taking differences of eigenvalues. So these differences of eigenvalues are the weights of the adjoint action, and those are the elements that I really want to consider. So these are lambda ij, they are again symmetric m minus first symmetric powers of elements of the m minus first symmetric power of the tangent space. So if m is greater than or equal to 2, so I'm at an irregular pole, a pole of a higher order, then of course these eigenvalues, they're not numbers, they are genuinely vector fields raised to some power, or whatever, tensors. So we introduced this concept called a Stokes vector. So it's a preferred, some kind of distinguished direction in the tangent space of x at P. And you define them like this. So V tangent vector is an ij Stokes vector if, when you raise it to the m minus first power, you get exactly the weight ij. So practically or pictorially, here's what this means. So if I look at the irregular locus, so these are the points where multiplicity is at least 2. And what I will do is I'll take my Riemann surface X and I'll take the real oriented blow up at all those irregular points. So so this is like what I call X tilde. I look at the blow up locus D irreg, and I pull that up, and just like with any real oriented blow up, each component, the preimage is just a circle. So basically the preimage of this irregular locus is a bunch of circles, and you should think of these circles as giving you directions which correspond to directions, or which correspond to vector fields in my tangent space at P. And so what you get is that these ij Stokes vectors give you preferred directions on this blow-up circle. And so here I denote them with these empty circles. And there's a certain number of them you can count. They always occur in even numbers because you have this kind of duality lambda ij, lambda ji. Those are just negatives of each other. And then they're always, maybe another thing to say, from the point of view of connections and more specifically differential equations, you could try to look at solutions to your differential equation and how they behave as I parallel transport them into the pole. And then these Stokes directions correspond to exactly to points of maximal, let me just write this properly. The points of maximal decay for preferred solutions, which have a kind of asymptotic behavior of the form lambda I, sorry, AI minus AJ over Z to M minus 1, where I'm thinking lambda I is a vector like this. Right. Okay. And then so you get these distinguished directions, which manifest themselves as distinguished points on these blow-up circles, and then they're always separated by kind of equidistantly by what are called oscillating directions, which are basically the directions where these preferred asymptotics of solutions, rather than having a point of maximal decay or maximal growth, they basically, they're like oscillatory functions. So the exponent here is purely imaginary. So that's why people call them oscillatory or oscillating directions. So I will denote them by these circles with a crossed circles. Okay. So basically, once you have a representation of your Lie algebroid, you restrict it to each irregular locus, you get these distinguished points on the blow-up circles. And I'll use these points to construct a graph, a certain graph. Okay, so let me make a few more assumptions. So if you assume that the polar data, which means this isotropy representation, is generic, which means it's some kind of assumption on the eigenvalues, and specifically in the case of simple poles, you just want the eigenvalues to have distinct real parts, and in the case of high order poles, you want the eigenvalues to be distinct. So it's some generic assumption. So if you make that assumption, then the number of these Stokes and oscillating directions is maximal. You can count how many weights you have, how many possible directions you could have. With this genericity assumption, you get all of them necessarily on your blow-up circle. And in the case that I care about, which is rank n equal to 2, there is the count is very simple, but there's 2 times m minus 1 of each kind. So there's 2 times m minus 1 of Stokes directions and of oscillating directions. Okay. Right. So another important thing that you get with this kind of genericity assumption is something about behavior of solutions near these Stokes directions or near simple poles. So it goes like this. So if I'm in a vicinity of a Stokes direction, or in some sector near a pole of order 1, then from kind of simple classical ODE considerations, you get that your bundle is filtered by growth rates as I take my solutions and parallel transport them into the pole. So some solutions grow faster than others. And these growth rates are somehow given exactly by these, the growth rates are given exactly by the eigenvalues of the isotropy representation. And therefore, kind of relative growth rates or understanding which solution grows faster than another, those are given precisely by the weights of the joint action. So these lambda ij's. So that's why you're focusing on the Stokes directions, and that's where you really get some kind of filtration. And these filtrations, well, they don't really have a name. I usually call them Levelt filtrations because he kind of considered them in a very systematic way in his thesis a long time ago. Right, and so from the point of view of representations, you could think that when I study these rank 1 algebroids given by a divisor, then any representation of it assuming some generosity assumptions, any representation is a kind of locally filtered representation. It has this canonical filtration, which is flat, and that's important. But it's only well defined near a first order pole or a Stokes direction. Of course, they're flat. These filtrations, which means I can parallel transport them, all across the surface away from poles. But that, of course, somehow depends on how I parallel transport them. I would need to choose a path. Right, but so that's why they're kind of only locally well defined, or only locally canonical. Right, and another point to say is that if I do assume this generic polar data, then these filtrations are in fact full. So they're one-step filtrations. So these are vector bundles of increasing rank by 1. Okay, so all this information that you get out of E nabla being a representation of my Lie algebra, you get this for free. It's just there sitting waiting for you. I'm going to use it. Okay, so now I want to define this combinatorial gadget, which will help me to Abelianize these connections, and it's called the Stokes graph. So now let me specialize to rank 2, so n is equal to 2. So Y is a ramified double cover, and again B and R are branch and ramification loci. Because n is equal to 2 and y and x are smooth Riemann surfaces, these are necessarily reduced divisors. Anyway, it doesn't matter. So then I want to make a couple of more assumptions. So first of all, I want to make sure that I'm separating the branch locus and the polar locus. There's no real harm in combining them, but then kind of the construction becomes more confusing. So I just want to separate them. And then the other thing is I want to kind of assume that my covering Riemann surface Y is large enough to be able to carry enough rank 1 representations such that I can recover all rank n representations. So by large enough Y, I just mean that it needs to have a big enough genus to be able to support enough rank 1 representations. And the kind of numerics works out to be that you want gy to be this number. So obviously some kind of Riemann-Roch and Riemann-Hurwitz calculation goes into this formula. Anyway, that's what you need to do. Right. So now I have all these points, all these distinguished points on my Riemann surface X, which are there are the branch points, there are the simple poles, there are also the irregular poles, which now I blow up and highlight some distinguished Stokes directions and oscillating directions. So those are going to be the vertices of a graph, and it's going to be a bipartite graph. So I want to give these vertices a color. So I've already been kind of doing it, but now so here it goes. So I introduced 2 colors for these points in B and D, and the colors are crossed circle and empty circle. They're colors, okay. So all the points, all the branch points are going to be crossed circles, and all the regular poles, so poles of order 1, they're going to be empty circles. And then I look at the blow up of the irregular locus. So on each circle, I have Stokes directions. Those are going to be empty circles for me. And I have the oscillating directions. Those are going to be the crossed circles. So those are the 2 colors. That's how I color them. So here's a definition. So this is the gadget that I need. So a Stokes graph with some adjectives, simple, saddle-free, doesn't really matter what they mean. So a Stokes graph, gamma, on this data, which is a pair of Riemann surface X with divisor D, adapted to my double cover pi. So it's a bipartite square graph on X with vertex colors as I just described, and which satisfy some rules. So maybe a couple of things I need to explain. So bipartite just means that all the edges go from one color to another, never from the same color, never connecting points of the same color. And square graph means that all the faces are quadrilaterals. So they have 4 edges and 4 vertices in its boundary. And because it's a bipartite square graph, it means it always has 2 vertices of one kind and 2 vertices of another kind. So they always look like this. So maybe I can draw. So all the faces, oops. All the faces look like this. So they're quadrilaterals with 4 edges and 4 vertices, 2 of each kind. Okay, and there are some rules that basically correspond to these adjectives that I kind of mentioned here in brackets. So first of all, at each branch point, I want these graphs to be trivalent, meaning that, so for example here, in this example, here is a branch point and you have exactly 3 edges coming out. So that's what we mean by trivalency. And then at each, so I also have these crossed points on the boundary of my real-oriented blow-up Riemann surface. Those I want to be bivalent, and the 2 edges being the boundary arcs. So here's looking at this example. Here I have one of these oscillating directions, and it's connected by 2 arcs, which are the boundary arcs for my real-oriented blow-up. So I want to count those as my edges, and the only edges which are incident to this vertex. Okay, so these are kind of actual examples of actual differential equations. So for example, this one, this is the Gauss hypergeometric equation. So I'm thinking that I'm on P1 and I have 3 simple poles. So it's a rank 2 connection. So these are the, so I have 3 simple poles, and this numerics that I mentioned here, so D has to be 3. So 3 minus 3 is 0. 4, and I'm on P1, so the genus of X is 0. So the genus of Y has to be 0. So what I'm looking at, the double cover is just a double cover of P1 over P1. And these are the 2 branch points of my double cover. This example, maybe a little bit more interesting. This is also on P1, and now I have 4 poles. Oops. I have 4 poles here, there, and there. Again, the numerics works out to be that, so looking at this equality again, so G is still 0, D is 4, and so 4 minus 3 is 1. So Y, my double cover, has to be an elliptic curve. So it's an elliptic curve sitting above P1, and therefore, as you would expect, you should have 4 branch points, and there they are, and each one is trivalent. Okay, so these are all examples of connections without higher order poles. So here is an example of a connection, of a picture that comes from a connection with a higher order pole. This example actually corresponds to the Bessel equation. So we know the Bessel equation is an equation on P1 with 2 singularities, one of them being a simple pole and one of them being an order 2 pole. So that's exactly what we're seeing here. Here's the simple pole. So it's just one circle. And this is my irregular pole. So I've already blown it up. And on the boundary circle of this blown up, real-oriented blow-up Riemann surface, I have the distinguished directions, 2 of them being the Stokes directions. That's where, the solutions to my Bessel equation experience some maximal decay or growth. And then there are these oscillating directions. And again, you can do the count. You will see that the curve Y has to be an elliptic curve. It has to be a P1. So this is again P1 over P1. And as you would expect, you should only get 2 branch points, and there they are. Okay, so that's how they kind of these pictures go. Any questions about the pictures? Okay, so oops. Right. Okay, so here's so what's the use of this Stokes graph? Yeah, so there's a couple of really useful things that you can do with it. And this is the genericity assumption that I need in order to proceed with Abelianization. So if I look at one of these faces, which is a quadrilateral, a diamond, then 2 of the vertices in this diamond, they are poles or Stokes directions. And as I explained, those are always equipped with these local Levelt filtrations, canonical flat filtrations. And they are, of course, as I said, they're only canonically defined, near these points. But because they're flat, I can analytically continue them, or I can parallel transport them anywhere I like. And in particular, because this diamond, so each face has the topology of a disk, it is really a disk, a simply connected space, I can always take these filtrations and parallel transport them over the entire face, and then compare them. And so what I want to require from my connections is that when I do that, when I take this green filtration and this blue filtration, and I compare them, that those 2 filtrations are transverse. Right. So when you make this assumption, then there's a key property that is used in the construction, which is that because my filtrations are transverse, this is basically now a question of flags, a transverse flags in a vector space. And there's one kind of very simple linear algebra fact that when you have a vector space, in fact, of any dimension, in this case, I'm kind of considering dimension 2, but of any dimension, if you have 2 transverse flags, intersecting them splits your vector space into a direct sum of lines. And so you get this, the same phenomenon here, that over each diamond, because I have 2 filtrations which are transverse, I intersect them, and that gives me a canonical decomposition of my vector bundle into a direct sum of flat line bundles. These are flat lines, so this is a flat decomposition. And so somehow the cool thing is that with this genericity assumption, my Riemann surface X is covered in these diamonds, funny looking diamonds, and over each diamond I have a decomposition, a flat decomposition into line bundles. The point, of course, is that these decompositions don't agree, because my filtrations don't agree, or they have monodromy or whatnot. So so when I look at 2 diamonds which are adjacent to one another, they have this edge running in between them, I can compare the 2 decompositions over the edge. And so I get these decomposition isomorphisms, which are just basically ratios of the 2 decompositions. And the cool thing is that because these filtrations, the way they're built, these filtrations are flat filtrations based, given by growth rates as I go into the pole. That means if I look at this diamond, I have one of the line bundles making up the filtration comes from the fact that I parallel transport my flat sections into this pole and look at growth rates. But then if I look at this diamond, I'm getting a line bundle which is the same. It's the same because in this decomposition, because I look at flat sections which I parallel transport and look at the growth rates, and I parallel transport both of these line bundles into the same pole, so they are the same. So and of course because these are flat isomorphisms, these comparison isomorphisms are flat, they necessarily have to preserve this growth kind of grading by growth. And so what you conclude is that these comparison isomorphisms are necessarily of this upper triangular form, where, you know, in the first entry, you just have the stupid identity because it's the same line bundle. But then, but then the other, you know, sections of the other line bundle, they could go in either direction. And okay, so, and this is basically kind of, these two observations are somehow the key to proceeding with the construction, because essentially what you do is I'm going to take these line bundles, these line bundles that are sitting in my decomposition, and I'm going to put them up, pull them up onto the double cover in an appropriate way. And then I'm going to use this other diagonal entry, Gij, which is an isomorphism going from this line bundle to this line bundle. I'm just going to use that as my gluing data. So I'm going to glue all these locally defined line bundles into a global line bundle on Y. And then, so in this procedure, the only thing that I'm kind of forgetting is this off-diagonal delta information. And that is used in order, that is precisely kind of going back to the question of Jan, this is precisely the data that seems to be completely standard that you can organize into a co-cycle which deforms the push-forward factor. Okay, I don't have much time left, so let me try to briskly explain you know, at least some things.
Don't worry too much about the time, right? We're always flexible during this seminar.
Oh, okay, that's great. That's awesome. Okay. Well, I guess so. Maybe like on the hour, we'll stop and let people who need to go, and then we can continue the discussion. So, okay, at least I'll certainly be able to kind of state the theorem. So the theorem is that, so now I'm defining properly these two categories that I mentioned before. So on the one hand, I have this category of rank 2 representations, and the genericity assumption that I specify is that I want those canonical locally defined Levelt filtrations to be generic with respect to this graph, so that over each diamond I get these flat decompositions. So this is really a genericity assumption, and there is maybe the proper way of saying it is it's kind of like it really captures almost all possible representations. The correct way of saying it is if you let's say descend down to you know, isomorphism classes of representation, so you're like on a moduli space, that thing has topology, and the subset cut out by these generic with respect to gamma connections or representations is a dense open subset. So the only thing you're not capturing is some kind of divisor. Yeah, harder to say at the level of categories. Anyway, so that's on the one hand, and on the other hand, over my curve, over my double cover, I look at rank 1 representations, and I want these to be singular along the pullback divisor with the same order singularity as my original connections. And also there is this additional thing, which is that they're all necessarily meromorphic along the branch, along the ramification locus, but the residue is somehow completely fixed. The residue is always, it turns out to be -1/2. And that is somehow directly related to the fact that this is a double cover, and in the kind of in the local coordinate near the branch point, the covering is literally kind of like z going to z squared. So this 2 in z squared is the same, is very much related to this 2. It's not the same 2, they're different 2s, but they're related. Okay, so those are the categories, and it turns out that there is a way to modify, to kind of deform locally the push forward functor pi lower star, such that you can set up an equivalence of these representations. So you take a rank 2 representation and you output a rank 1 representation, and you can go back. So just a couple of remarks, and then I'll stop. So that's I already said, the kind of equivalence, the inverse equivalence to going back is really it's almost the push forward functor, but somehow it's deformed in a local sense by certain canonical groupoid cocycles. So you deform it to a new functor, and that new functor, which I call pi ab gamma, is a kind of de-abelianization functor. That one lands in the right place and actually inverts this abelianization functor. Right. Actually, probably this is a good point to stop and let people ask questions, and then I can maybe say a few more things for the people who are interested.
All right, but let's first thank Nikita for the